We're going to take a look at conditional probability again. So this is the second set. Mr. Squirrel is going to remind us here, this is part 2 of the 4.4 section of our textbook, which in my lesson series is 1.5. So conditional probability is this idea that your knowledge of something changes the probabilities of the potential outcomes. And it's written such that, probability of event B given that event A has occurred. So you're going to be told that something is true or that something is not true, and that changes the possibilities of what's about to happen. As an example, what if I said I wanted a jack? Now, jacks are face cards, so to say face card and jack is pretty simple. And what if I told you I've already pulled the card, I'm looking at it, you don't get to see it, and it is in fact a face card. What's the probability that it's then going to be a jack? So in this example, B is the probability of it being a jack. So let me just switch over here to just a blank slate. So if I said the probability of pulling a jack given that it is in fact a face card means that I've got prior knowledge. I know it's a face card. And so the probability of actually getting a face card is 12 out of 52 because there are 12 face cards in a deck of 52 cards. The probability of it being a jack and a face card is 4 out of 52 because there are 4 jacks in a deck. Now, the reason why I'm dividing this is because I already know it's a face card. I don't have to worry about this very low probability of it being a jack because I have new information. All of the number of cards and the aces can be thrown right out, and I can just focus on the 12. And so, in fact, when we do this division, what ends up happening is, of course, you multiply your reciprocal of the second fraction. We end up with something like this, and the 52s will effectively divide out to a 1, leaving us with 4 over 12, and 4 over 12 simplifies to 1/3. So originally, my chances were pretty low that this was a jack. I mean, 4 out of 52, not great odds here, not great probability, but because it's a face card and there's only 12 face cards, I have a 1/3 chance this is a jack. There's 4 jacks, there's 4 queens, and there's 4 kings. So I have a 1/3 chance if you really just want to look at it this way, because I told you it is a face card. Well, what if we weren't looking for that piece of the equation? So the equation is just up here in the top right-hand corner. What if I rearrange it? What if I say that, I know the outcome probability, I'd like to know the original probability, or something along those lines? Well, algebra allows us to switch the equation around. So if I multiply both sides of the equation by the denominator, I get the probability of B given A times the probability of A is equal to the intersection probability. It's a lot of math speak and a lot of blah, blah, blah for I can multiply equations. It goes back to something where if I had, let me just scroll past this section. So if I had, m over x equals y, just random letters, then I can multiply both sides by x so that it is m equals y times x, similar to your velocity and time and stuff. Well, when this is used when we're considering more than one event happening at the same time, and the second event might depend on the first event. So what if I want to draw a jack and then draw an ace, or pull out a blue marble and then a black marble? So the best way to look at this is with examples. So we're going to go with this. Hoger's friend assures him, or Hoger's friends rather, assure him that if he asks Julie out on a date, there's an 85% chance that she will say yes to him asking her out. But this requires him to actually ask her out. We don't know for a fact that he will. See, in the previous examples, you would be given, okay, Hoger's going to ask her out. But in this case, we don't know for sure that he is. So we're also then saying if there's a 60% chance that Hoger will summon the courage to ask Julie out next week, what is the probability they will actually go out? Let's take a look at this mathematically. We'll say H is the event that Hoger asks Julie out, and J is the event that Julie says yes. What do we know? What do we already know? Well, we know that there's a 60% chance or probability that Hoger will get the nerve to ask Julie out. Now, if he asks her out, there's a really good chance she'll say yes. That's the fact that his friends told him, listen, if you ask her out, she will probably say yes. There's an 85% chance she'll say yes. But because it's an if you ask her out, we're not saying, J and H. Not yet, because that's the thing we don't know. All right, so here's our original equation, and we can rearrange that equation and put the appropriate letters in it so that the P of H, which would have normally been in the denominator, gets multiplied on both sides and is over here. So I end up with the probability that Hoger asks out Julie and Julie says yes, because don't forget that's what those letters stood for, is equal to the probability that Julie says yes, given that Hoger asks, times the probability that Hoger even gets the guts to ask her out in the first place, which is now just a matter of doing the math, which is a 51% chance. And when you think about it, that feels really low. It feels really low when you know that the original probability, as friends said, you've got an 85% chance she'll say yes. But the reason why it's so low is because he has to get the nerve to actually ask her. There's only a 60% chance he'll ask her to begin with. Now, if there's only a 60% chance that he'll ask her to begin with, and then there's a 15% chance she'll say no, it reduces the probability from the 60% just a bit, effectively by 9, because she might not say yes, and he has to get that courage to ask her out. So therefore, the probability of seeing them together on a date is 51 or 0.51 or 51%. Okay, let's take a look at a second example. So the probability that some woman, Sue, will go to McGill University is 1/5. The probability that she'll go to the University of Ottawa is 1/2. There's a better probability that she'll stay home. It's cheaper, she gets to be with her family and free food and all of that stuff. But if Sue does decide to go to McGill, which again is a 1/5 chance, the probability that her boyfriend Bob will follow her is 3/4. So a pretty good chance, actually. So Bob's basically saying, listen, if you decide to go to McGill, I'm probably going to follow you there. There's a 75% chance I'll follow you there. So what's the probability that they will both end up at McGill? Kind of similar to the Hoger asking Julie out on a date scenario. So we're going to say A is the event that Sue goes to McGill. B is the event that Bob goes to McGill as well. So the probability that Bob will go to McGill depends on Sue going. And so he said there's a 75% chance or 3/4 chance that I'll go too. Okay, if you go, I'll go. But she's not so sure she wants to go in the first place. It's scary, it's far away, it's very expensive. Well, what's the probability that they both end up at McGill, which is this intersection or the and? So we've rearranged the equation again, and we're just going to fill in the numbers. So 3/4 for Bob going to McGill if she goes to McGill as well, and times the probability that she's going to go in the first place. So 3/4 times 1/5 gives us 3/20, which is not great chance. It's a 15% chance, I believe. And 15% chance that she'll go, and that they'll both go rather, and that's because she's really not sure to begin with. I mean, there's only a 20% chance she's going to go to begin with, and then couple that with the fact that there's only a 75, I say only, but there's a 75% chance that he'll go if she goes. So it drops her percent from 20 down to 15, which, if you really think about it, makes sense. 75% of 20 is 15. So I've got some recommended questions here for you to do from the textbook, and Mr. Squirrel is definitely reminding us that we could have quizzes at any moment, so maybe we might have a quiz the next time I see you. So that's Conditional Probability Part 2.